Hello, my dear students. My name is Josiah Mwaktalima. I'm a chemist teacher. I'm here today to proceed with our discussion on chemistry subjects. And specifically for today, we are going to discuss on a topic known as electrochemistry and a subtopic known as Nernst Equation. It is a continuation of where we ended. So you are welcome. Keep on following me. Now let us write. The topic is electrochemistry. And our subtopic is Nernst equation. So by the end of this lesson, you will be able to use the standard electrode potential in determination of pH of a solution, but you also will be able to use the standard electrode potential to predict if the chemical reaction can take place or cannot take place. That is the feasibility of the reaction or the unfeasibility of the reaction. So that is the main object that you need to consider it and be able to do those questions. So these are the two main major objectives that you need to attain at the end of this lesson. Now, if we go back on the application of standard electrode potential, we said that it is used in prediction of the occurrence of the reaction, determination of pH of the solution, construction of electrochemical cell, as well as in determination or in using it in determination of electrochemical, in placement of an electron or an ions in the electrochemical cell. So let us now start with the determination of pH of a solution. Normally, a pH of a solution is being determined or measured by a specific device known as pH meter. So now, if you don't have a pH meter, how can you measure or determine the pH of that solution? Here, the standard electrode potential can help you on determination of the pH of the solution. So let us see the procedures of how can you determine now the pH of the solution by using the standard electrode potential. Normally, in determining the pH of a solution, you must have two electrodes. And one of the electrode must be the hydrogen electrode. And the second electrode is known as the standard electrode. And the standard electrode is the one with known EMF of that electrode. So requirements now here. One, you must have the hydrogen electrode. And the hydrogen electrode, it must be dipped into a solution with a known pH. So this one is dipped into a solution of unknown pH, which means that the solution which is now required to determine its pH. And the second, you must have a standard electrode, That means if the electrode with the non-standard electrode potential. And this standard electrode must be dipped into a solution with 1 molar concentration. So this one is dipped a solution of 1 molar. So these are the two main requirements when you want to determine the pH of a solution. You must have the hydrogen electrode and the standard electrode. So let us now consider if we have our non-electrode or our standard electrode as silver. Consider you have silver electrode whose standard electrode potential is 0.8 voltage. And you have the hydrogen electrode which have its standard electrode potential is 0. So to construct a cell, so the hydrogen, the standard electrode potential of hydrogen electrode is 0.00 voltage. So now you have to construct a cell by using two electrodes that have been mentioned. So here it can be any other electrode apart from silver. It will depend on the standard electrode that you have been given. So here we have our electrode which is that of silver and that of hydrogen. So let us go now to construct our cell. And remember, we also discussed this on how to construct a cell since it is a revision. So you can construct an electrochemical cell by using those two electrodes. So here you must find out which electrode is more reactive and which electrode is less reactive. And you remember the electrode which is more reactive is always placed on the left side, and the electrode which is less reactive is placed on the right. So here hydrogen electrode is more reactive because it has less positive than silver. So hydrogen electrode will be placed on the left. So our electrochemical cell, if we sketch now, that means you will be having the voltmeter that will be reading the EMF of a cell. Then here we have the hydrogen electrode, and you remember the hydrogen electrode, we have said that it must be placed in a solution with unknown pH. So this is hydrogen electrode, and the hydrogen gas is being introduced here, and this is now our solution with the unknown pH. And also the silver, which is our standard electrode, must be placed on the right side since it is less reactive than hydrogen. So you'll have another electrode which is silver that is placed on the right, but it must be dipped into a solution of its ions, which means that if you take silver nitrate, but the solution must be 1 mole its concentration. Now, here we must have the Soti bridge. I know you remember the use of Soti bridge. For complete the circuit of the cell. Now, since hydrogen is the more the more reactive electrode, it will be releasing electrons. So electrons will be moving in that direction, and the current will be moving in opposite to the movement of. So this is now also silver electrode. So this is voltmeter. That reads the EMF of a cell that can be produced in that electrochemical cell. So let us now consider how do we determine the EMF of a cell, which means that we can go back to the application of Nernst equation. So in our example, the E of a cell is determined by taking E of silver minus E of hydrogen. That is how we can determine the E of a cell. But if we call back, if we call about the Nernst equation, the E of hydrogen is determined by taking the E standard electrode potential of hydrogen, which then will be minus the 0.059 log of concentration of hydrogen ions. I know you remember this when we were starting discussing about the standard electrode potential or the application of Nernst equation. Now, if we substitute now this value to that, which means that here this one is positive. So if we substitute, the E of a cell will be equal to standard electrode potential, then of silver will be minus that of hydrogen, which is E then plus 0.059 log of concentration of hydrogen ions. Okay, but remember that the E of hydrogen is equal to 0.00 volts. So which means that our equation now on E of a cell will be equal to, from there if we substitute 0 there, will be this one parameter which is now 0 minus that one. So this will be 0 minus, so it will be E standard electrode potential of silver will now be minus 0.059 then log of concentration of hydrogen ions. Now from that equation, if we make log of concentration of hydrogen the subject, then E of a cell will be equal to, will be minus standard electrode potential of silver, and then will be equal to negative 0.059 log of concentration of hydrogen ions. And if we divide by negative sign throughout the equation, then in this side you'll have E of silver will be minus standard EMF of a cell, then will be equal to 0.059 log of concentration of hydrogen ions. So let us now divide by 0.059 in both sides. So if we divide by 0.059 on both sides, then you have E of silver minus E of cell, then will be equal to divide by 0.059, then will be equal to log of concentration of hydrogen ions. Now from that equation, let us multiply by negative sign on both sides so that you can get the negative log of concentration of hydrogen ions, which will be our pH. So if we multiply, this equation now will be E of cell then divide by 0.059, then will be equal to log, negative log of concentration of hydrogen ions. But if we recall now, from negative log of concentration of hydrogen ions, this one is equal to the pH. So now the pH will be equal to E of cell then minus standard electrode potential of silver, then divide by 0.059. So this is our equation that can be used to calculate the pH of a solution. So remember that this equation is only specific for the electrode or for the electrochemical cell, which is made up of silver and hydrogen electrode. So if it is another electrode, that means you have to derive the formula for each electrochemical cell. And so you have to consider this. Be careful with this part. For each electrochemical cell, when you're finding the pH of that solution, you must derive its formula. Now, from this part now, you can be able to find the pH of the solution, since the E of a cell will be ready from the electrochemical cell by using a voltmeter, and the standard electrode potential of silver is the standard electrode. So its EMF or its electrode potential will be given. Then you divide by 0.059, then get the pH of that solution. So now here you have determined the pH of a solution without using a pH meter, which is an instrument mainly used for measuring the pH of any solution. So that is end about how to determine the pH of the solution. So let us consider another part, which is an application also of standard electrode potential, which is the prediction of the feasibility or occurrence of a reaction. How can you predict, or how can you know that this reaction will take place or will occur and this reaction will not occur? Then by using standard electrode potential, you can be able to judge that statement, whether the reaction will take place or will not take place. So prediction of the occurrence or feasibility of the reaction by using standard electrode potential. Under this part, you will be given the redox reaction, which now you will be asked to judge if the reaction will take place or will not take place. So consider the reaction A, then with B, then reacting to form A, then plus B, that one. Then you may be asked to determine if the reaction will occur or will not occur. That is the feasibility of the reaction. Now, for this part, you will also be given the standard reduction potential of each cell. For example, here, let's say that you have given the standard electrode potential of given the reduction potential of A, let's say it is negative 0.77 voltage, and we have that of B let us change this one here instead of being 5 because it is a redox. So this will be 3 positive and there will be 5 positive. So if here you have 5 positive, then plus 3 plus 2 electrons, then be 3 positive, then its standard electrode potential, let it be 0.33 voltage. These are the given reduction potential. Then you have been asked to predict if the reaction, this one, will be feasible or will not be feasible. Now the procedure to follow when given such a question is that first you have to write the half reaction equations as they appear in a given equation. So this is our given equation. So if we write the half equation for the given redox reaction, that means for is A positive 2, then plus 2 electrons gives A. That is the first half equation. The second half equation is B3 positive to produce B5 positive. So it will be B3 positive, then leads into formation of B5 positive, then it will be plus 2 electrons. So these are the two half equations that are being formulated from the given equation. Now the second part is that you have to compare. You have to compare the half equation that you have obtained with the half equations with the standard electrode potential given. So compare with the given reduction with the given half reduction equations with the given half equations. Whereby here A is being reduced, but B is being oxidized. But in our given half equations, A has been reduced. It is the same to the one that we have obtained it from that reaction. And B has been reduced, but in our equation B is oxidized. So once the given reduction equations appear in opposite to that which have been formulated from the equation that you are asked to predict if it occurs or not occurs, then you have to change their sign. So if it appear in opposite, then you have to change the sign of that reaction. So here, this B is in opposite, appear in opposite to this one. So the given standard electrode potential, its sign will be changed. So the standard electrode potential here will be positive 0.33 voltage. Now from there, you have to obtain the sum of the standard electrode potential, which means that here E total will be equal to, now we have 0.77 negative, so it's negative 0.77 voltage. Then it will be plus, it's a sum or summation, is 0.33 voltage. So the sum of this one you'll get will be negative 0.44 voltage. Now, after getting the sum of the standard electrode potential, then is there now you can judge if the reaction will take place or will not take place. If the obtained sum of the standard electrode potential is negative, that means the reaction is not feasible. But if the sum of the standard electrode potential obtained is positive, then that reaction will be feasible. From there now we can conclude to our equation, which means that this reaction is now not feasible. So that means you have now used your standard electrode potential to decide if the reaction will occur or will not occur. So our reaction now is not feasible. What have helped you to judge if it is feasible or not feasible is the standard electrode potential. So that is how you can use the standard electrode potential to determine or to predict the feasibility of the reaction. So from there now, after a short break, we will be back for some questions on how can we use this knowledge. So see you later. Thank you. Okay, welcome back now for discussion on some questions that employ you to use the knowledge that you have discussed. And the first question is that you have been asked to explain briefly how can you determine the pH of a solution from standard electrode potential without using a pH meter. So it's an explanation equation. So you need to give up the highlights on how can you determine the pH of a solution without using a pH meter. So in this question, the hints that you are supposed to consider is that first, you must have a standard electrode potential, and that one must be with a known standard electrodes. And the second, you must also have the hydrogen electrode. So the standard electrode and the hydrogen electrode. And the hydrogen electrode must be dipped into a solution of unknown pH. But the standard electrode must be dipped into a solution of 1 molar containing its ions. And from there, you have now to derive the equation. And by considering those points, then you will be able to get the marks from that equation that you have been asked to explain how can you determine the pH of a solution without the use of pH meter. And part B, you are asked to calculate the pH of the following cell, which is that of hydrogen and that of silver. And given the E standard electrode potential of a cell, this is the standard electrode potential, this is the electrode potential of a cell. And you have been given the standard electrode potential of silver. If you remember from our derivation, we said that the pH, since it is silver and hydrogen, there is no need of deriving the equation. But if it is you have to derive it. But since we have derived it here, then you can is equal to constant E of, we derive that it is E of silver, then minus E of a cell, standard electrode potential of a cell, then minus standard electrode potential of silver. Then we said it is by dividing it by 0.0591. Now, given the data we have is E of cell, which is 1.22 voltage, and the standard electrode potential of silver is given as 0.80 voltage. So if we substitute now these values in our equation, then the pH will be equal to E of a cell, which is 1.22, then will be minus E of silver is 0.8. These are voltage, then divided by 0.0591. So Take your calculator now, my dear students, and feed this data into your calculator so that you can prove if you have the same answer as my answer, which means that it is 1.22 minus 0.8, which is equal to 0.42, and divide it by 0.059. The answer is 7.12. So our pH now here will be equal to 7.12. That will be now the pH of that solution through which now the hydrogen electrode is immersed into that solution. Hello students, let us now go and consider example number 2. And example number 2 is concerned with the determination or the judgment of a reaction. Once you have been given the reaction, then you are asked to judge if the reaction will take place or will not take place. So our question is that predict whether or not the following reactions will occur in 1 molar solutions by using the data given in the table below these questions. So we have A, B, and C. So for myself, I'm going to do part A. So the other parts now you'll go and do it for your own time. So let us now proceed with the part A. So the given equation is what I said is iron 2 aqueous that reacts with the chromium 3 aqueous, then to form iron 3 aqueous and the chromium 2 aqueous. So this is our redox reaction. As you if you remember, I told you that here you have first to write the half equations from the given reaction equation. So the half equations here, the half equations, this is one is the conversion of iron 2 to iron 3. So iron 2 to iron 3. Then when balancing now the charges that you have to add 1 electron there. And the second half equation is the conversion now of chromium 3 to chromium 2. Chromium 3 then will be plus 1 electron to balance. Then the product is chromium 2 ions. So these are our half equations. So once you have been now formulated your half equation from the given equation, we have now to go and compare this half equation to the given half equation with their standard electrode potential. So let us now consider now from the given half equations Okay, now let us compare our half equations from the given reduction half equations of our half cells. So if we observe now, we have iron 2 that have changed into iron 3. But our given half equation for iron is from iron 3 plus electron to iron 2 aqueous, and its standard electrode potential is positive. .771, and our second half equation is chromium 3 to chromium 2. But let us now compare it with our half cell reduction equation, which is now for chromium. Here we have been given it is from chromium 3 to chromium 2, and its standard electrode potential is negative 0.408. So we have chromium 3, then into chromium 2, and its standard electrode potential given as negative 0.408. Now, in comparison, the half equations from our given equation for iron is in opposite to that of reduction half cell equation that we have been given there. So now the standard electrode potential for iron now will be changed its sign from positive to negative. So if it's from positive to negative, now we can now convert So after conversion now, then you have to find out the E total. And the E total now here will be the summation of the standard electrode potential of the two half cells. So for iron now will be negative 0.771, then summation that will be plus negative then 0.408. So if we find it, then you'll have, now using your calculator, will be negative 0.771, then you also will be minus 0.408. Now our answer here is negative 1.179 voltage. So now that is the E total of our equation. So if you remember, I told you at the beginning that here now you can now judge if our reaction will be feasible or will not be feasible. Now we said that if it is negative, the E total is negative, then our equation will not be feasible. If it's positive, then our equation will be feasible. So here now you can judge now from that E total that our equation given here, reaction, so this equation now is not feasible. Why not feasible? Because the E total obtained is negative 1.179 voltage. So that is how you can predict if the reaction will be feasible or will not be feasible. Now, if we go now to compare the normal application to our life situation of standard electrode potential, is that we are using a lot of different materials that are made up of metals, and each metal have its standard reduction potential. So how can you now prevent those metals from corrosion? Because we have seen that most of our material are being corroded because of the chemical reactions which are taking place in those metals, and those chemical reactions are redox reactions. So here, by using standard electrode potential, you can know now a suitable metal to plate or to electroplate your metal so that you can prevent it from rusting. And a good example is that nowadays our corrugated iron sheets that we are using them in buildings are being plated or are being painted. The aim of painting is not just for decoration, it's also for preventing them from being corroded or from rusting, because a good example of corrosion is rusting of iron. So we can now use a suitable, or you can select a suitable metal that will now help you to prevent the other substances which are most useful in our life situation from rusting. And also, we have seen that we have different materials. For example, the most commonly used metal in electroplating, we mainly use zinc. But for vessels which are being used in carrying food substances, we prefer to use nickel. Why do we prefer to use nickel? Because nickel is non-toxic. So even if you carry food inside those vessels that have been electroplated by tin, then you'll be safe, the food will be safe and being eaten by we all. So from there now, that is the application of standard electrode potential. So what do? You consider the metal or the element which is less reactive than the metal that you want to electroplate it. And after using that, then you'll be now able to use that metal without any correction. So from there now, we have some assignment that I will now give to you, that the second question is this one, that you are given iron 2, those redox reactions 1, 2, 3, and from those data, you are asked to use the given reduction potential to account for the following observations. Here, A is that a pale blue solution of copper 2 sulfate disappears when iron rod is dipped in it. So the standard electrode potential will help you to answer such kind of question. But part B is that it is improper to use nickel knife spatula to stir a solution of copper 2 sulfate is also the application of standard electrode potential. So that is the second assignment. Do you remember the first one is that I left for you those the two parts from the example that I did. Now another question is that calculate the pH of the following cells. This is for application of standard electrode potential. What we have discussed, that it is applied in determination of pH of a solution without using a pH meter. Now our first cell is this one. You have been given the EMF of a cell, which is 0.89 voltage, and E, standard electrode potential of gold, is 0.55 volt. So you can determine its pH. But the part B, you are given the half cell of the cell of iron and hydrogen, and the data given that you have the EMF of a cell, which is 0.22 volts, and you have the standard electrode potential of iron, which is negative 0.44 voltage. So that is another question now which I leave to you as an assignment, and after doing it, you can consult it through my number, which is 0713 14 09 14. I repeat, 0713 14 09 14. So then if you get the correct answer, then I'll tell you if it's correct or not correct. So that is now the end of our discussions today. So see you next period. Thank you very much.